In this video, we're going to talk some more about how conservation of angular momentum works. One of the things we talked about in the last DL is the relationship between angular momentum and linear momentum. They're very similar in most of the equations. In fact, the equations for angular momentum look identical to the equations for linear momentum. The only difference is that with angular momentum, we use slightly different quantities. For example, we know that the linear momentum of an object is equal to its mass times its velocity. What is the angular momentum of an object equal to? For reasons unknown, we represent angular momentum with a capital L. It's equal to I times omega. I is called the moment of inertia of the object, and it plays the role of mass in angular momentum. Omega is called the angular velocity of the object, and it plays the role that velocity played in linear momentum. Let's take a brief moment to talk about the moment of inertia. The moment of inertia is related to the mass of an object, but it's also related to the shape of the object. For this reason, we're not going to go over the details of how to calculate the moment of inertia for various shapes. It requires some calculus. We'll always give you the moment of inertia for an object, except for in one case. That case is the case of a point mass. As an example, let's just imagine a ball on a string. Let's imagine that this ball is rotating this way. What is its moment of inertia? We can assume that the moment of inertia of the string is so small that we don't need to care about it. We can basically treat the ball as a point mass. In other words, we can pretend that all its mass is in a single spot. The moment of inertia of a point mass is just equal to its mass times its distance away from the center of rotation squared. The center of rotation is here. So the distance is just the length of the spring, and the mass is just whatever the mass is. The nice thing about moments of inertia is they just add up. You can determine the moment of inertia of all of the individual pieces of a system separately, and then just add them up in order to find the total moment of inertia. So, for example, if we had a second ball on this string that was located here, we could just find its moment of inertia separately and add it on. Now let's talk about the conservation of angular momentum. We talked a lot in last DL about what happens when we apply torques on a system. If there is a net torque on the system, then the angular momentum of the system will change. But let's think about some cases where there's no net torque on the system. Specifically, let's think about the examples that we did earlier when I was sitting on the rotating chair. Let's start with the case of the two weights. In this system, there is no torque acting. Once I start spinning on the stool, we're allowed to just spin freely. There's nothing outside of us that is applying a torque. So the change in angular momentum for the system should always be zero. But what happens if I take the two weights that I'm holding here and move them out? For this example, let's just think about the weights as a point mass. While they're of course not a point mass, it actually turns out to be a reasonably good approximation. We already know what the moment of inertia of a point mass is. It's just the mass times the distance away from the center of rotation squared. So what happens to the inertia of the system if I take these weights and go like this? Well, their mass obviously is not changing, but their distance from the center of rotation is changing. It's getting greater. So I, the moment of inertia of the entire system, including me, the stool, and the weights, increases significantly when I go like this. But what do we know about the total angular momentum? Well, we know that it has to remain a constant. There are no external torques acting on this system. Here's the definition of angular momentum. If angular momentum is not changing, but the moment of inertia of our system is changing, then what must happen to the angular speed? Well, it must change as well. Specifically, if we're increasing the moment of inertia by holding the weights out, the angular speed must decrease in order to compensate. Again, it's not that any torques or anything was applied to cause me to slow down. It's just that my moment of inertia changed. And since the universe demands that the angular momentum remain the same, then my angular speed had to go down in order to compensate. In other words, I spun more slowly. But what happened once I brought the weights back in? Well, my moment of inertia would then go down, and so my angular speed would jump back up to what it was previously. Let's also look at the demonstration where I held the spinning bicycle wheel vertically and then started turning it. Let's try to work out why the chair started moving when I did this. This is a side view of the bicycle wheel. The bicycle wheel is spinning, and so it has angular momentum. What direction does this angular momentum point? We know that we're looking at this wheel from the side, so we expect the angular momentum to be pointing up or down. Let's say that it's pointing up. In other words, that from our perspective, the wheel is rotating from left to right. Now let's consider what happens if we rotate the wheel. If we rotate the wheel, the angular momentum will no longer be pointing in the same direction. It's always going to be pointing along the axle of the wheel. So if the axle has been tilted, the angular momentum will be tilted as well. Now up to this point, nothing strange has happened. In order for the wheel to rotate like this, the person holding onto it has to apply a torque to it. So there's nothing weird going on yet. But what happens if we include the person and the stool in our system? Conservation of angular momentum applies here because there's no outside torque on that entire system. So here, the angular momentum is pointing up. But over here, the angular momentum is now pointing up and to the right. But what do we know about the system? Well, we know that the overall angular momentum has to remain constant. After all, if we include the person and the stool in our system, then there's nothing providing an external torque in this direction. But if the only thing that happens is this wheel is rotated, then the angular momentum of the system is changing. It was originally pointing up, and now it's pointing sort of up and to the right. Remember, it's okay for the angular momentum of the individual parts of the system to change, but they have to change in such a way that the total angular momentum remains the same. In other words, all the changes have to cancel out. Because the angular momentum of the wheel in the vertical direction has been decreased, the angular momentum of me plus the chair in the vertical direction must increase. In other words, once the person sitting in the chair has rotated the wheel, they will have picked up some of that angular momentum. If the person plus the stool has an angular momentum upwards, that means they're going to start rotating. As with regular momentum, we can represent angular momentum with a momentum chart. Let's try to fill out a momentum chart for this case. But before we do that, I want to point out a subtlety here. Notice that initially there is no component of the angular momentum pointing in the horizontal direction. But here, there is a component of the angular momentum pointing in the horizontal direction. It's a component of the wheel's angular momentum. So it's not exactly correct to say that no torque is being applied to the system. There is actually a torque that's being applied from the ground on the stool. But because of the way the system is set up, we can't actually see the effects of that torque. And so we're not going to worry about it here. We're only going to be worrying about the component of angular momentum in the vertical direction. Let's draw out our momentum chart. Let's start with the initial angular momentum. What's the initial angular momentum for the wheel? Well, we already decided that it points straight up. What about the angular momentum for me and the stool? Well, initially, the stool was not rotating, so the angular momentum is 0. We now take the wheel and rotate it like this. What is the change in angular momentum for the wheel? Well, remember that we're only thinking about the vertical pieces in this problem. If the angular momentum initially points straight up, and then we turn it so that it's now pointing up and to the right, the vertical piece of the angular momentum is getting smaller. Notice the wheel still does have some angular momentum in the vertical direction, it's just not as much as it was before. But what must our change in angular momentum be for the whole system? In the vertical direction, it must be 0. There are no torques acting on the system that can affect the vertical component of angular momentum. So what must the change in angular momentum in the vertical direction be for me and the stool? The answer is it just has to be equal to and opposite the change in the angular momentum in the vertical direction for the wheel. The prediction, therefore, is that me and the stool will have some angular momentum in the vertical direction once the wheel has been rotated. And that's exactly what we saw. As an exercise, try to do this analysis for the second case, where I held the wheel stationary and then started spinning it. Next TL, we're going to move a step further in our analysis of momentum. We've talked about impulse as it relates to changes in momentum. But next DL, we're going to see the effect that forces have on an object more directly. We're going to study what's known as Newton's second law.